You already know a lot about cardiac muscle, smooth muscle. We're going to be putting these things to use. Before I go on, I have a question to you as students of Erland College. The faculty meeting that I was at just before coming to class, there was a discussion about the calendar for next year. Some of you are not impacted by the calendar for next year, and some of you are. There is quite a lot of, pros and cons about the two calendar options for next year. One is to continue with the 7-week term option, and the other is to go back to a 15-week semester option. Faculty are completely on one side or completely on the other side, or, I can see it both ways. I'm curious about how you see it as students, but rather than having this conversation, I invite you to use the forum to communicate with me and with each other about your opinions about which is better for students. Just assume that you are a representative student. What's better for you, and apply it. I'm curious to know what you think is better for the college and for students in general. 7 weeks or semesters. Just let me know through the anonymous or identified form. I'm really curious. Yeah.
When does that decision have to be made?
So what I learned in the faculty meeting is that it has to be made by February because future students want to know what's the calendar going to be like. So there was some talk about actually deciding in faculty meeting today, but I didn't quite understand why we would need to decide at the beginning of October if the real deadline is in February. So I had to leave the meeting to come here and get ready. So if the faculty decided that this conversation is completely moot, but based on what I was hearing as I left the meeting, I was hearing that we didn't have a consensus, that clearly there was going to be more conversation, more data gathering, and that's why I'm asking for you, just to, if you have a strong opinion, or even if you have a weak opinion, to let me know. You probably know I don't have skin in this game either, so my voice is completely worthless. But I can communicate with people in biology whose voices are not worthless.
Are students involved in the faculty meetings?
There are 2 student representatives from your student government,
Okay.
and I can't remember their names.
Okay. Well, at least we have some.
Oh, one is Maya Payne. That's one name that I was really, it's a pretty distinctive name. That was one of the student representatives. So that's another way to have input. Anyway, I'm really just curious. Okay, cardiovascular system. So we're taking a big step here away from cells and now building a system out of these cells. So, and I'm going to sort of be going back and forth between cells and the whole system. So you're going to have to try to keep up with, is he talking about one cell at a time, or is he talking about the whole heart? Is he talking about one smooth muscle cell, or is he talking about the whole, aorta? I'll try to be clear about it when I go back and forth. Okay, now we're big view, big overview. Heart. The heart is actually 2 pumps. There's a right pump and a left pump. And in most of your books, the right pump is blue and the left pump is red. But that's artificial, of course, right? In the body, it's going to look exactly the same. There's no blue side and red side. This blue and red is trying to emphasize the point that the right heart is pumping deoxygenated blood, and the left heart, the left pump, is pumping oxygenated blood. So you may know that arterial oxygenated blood is bright red, and deoxygenated venous blood is dull red. It's not blue. Dull red, bright red. Low oxygen content, high oxygen content. This is actually, so if you get a pulse oximeter and it's reading your blood oxygenation level, one of those devices for determining whether your blood is well oxygenated, it's really just measuring the color of your blood. How many of you have used a pulse oximeter to measure either your pulse or the blood oxygen content of the oxygen content of your blood? Yeah, I have two.
I do. The doctor in the hospital.
Oh, of course, right. And so I've got a little, handheld unit that I bought at CVS this week, just in case. And if you want to know your blood oxygen, I'll bring it in. I'm happy to bring it in. It's about the size of a ring box for a wedding ring. Okay. So sometimes I will talk about the left heart, or the right heart and the left heart. Of course, there aren't two hearts. It's the right side of the heart and the left side of the heart. The right pump and the left pump. Okay. So we're going to talk about the anatomy in the next couple of slides. The right heart pumps deoxygenated blood to the lungs, where it's going to release carbon dioxide and pick up oxygen. And that's going to be an important concept for respiratory physiology. We've got to put that aside. Except to know that the lungs is where we release carbon dioxide, exhale, and we inhale and pick up oxygen. Oxygenated blood is returned to the left heart, the left side of the heart, and pumped to the systemic circulation. Pumped to what are these supposed to be? These are various circulatory beds. So, for example, this might be a cartoon that illustrates the blood to the muscles. And this might be a cartoon that cartoons the blood going to the digestive tract. And this, let's just say, could be the blood going to the kidneys, right? Or the brain, right? So there could be another bed up here. So this is highly cartoonized. But oxygenated blood goes to the muscle, to the brain, to the muscles, to the digestive tract, to the kidneys, where nutrients and oxygen are provided to these metabolically active tissues. And carbon dioxide, as a byproduct of cellular metabolism and other metabolites, are picked up and returned to the right heart for doing it again. The heart also has, so there's two sides, right and left, and on each side there are two chambers. An upper chamber called the atrium and a lower chamber called the ventricle. The atrium, sort of like the atrium of a building, is the receiving area. And the ventricle is what does the work of pumping. So the right ventricle pumps the blood to the lungs, and the left ventricle pumps the blood to the body. So have we talked about all these things? We've talked about the left and the right. We've talked about the atrium and ventricles. We've talked about the pulmonary and the systemic circulation. Pulmonary is just referring to lungs. Systemic is referring to everything except for the lungs. So the brain circulation, or the muscle circulation, or the digestive tract circulation is part of the systemic circulation. Oh, so I haven't mentioned arteries and veins. There's a strict definition. So there's the common definition that you think of, and there's the strict definition that is correct. So so you would think, okay, this is an artery because it's carrying oxygenated blood. That's the common knowledge. But this is an artery that is carrying deoxygenated blood. So the way to think about it correctly is that arteries carry blood away from the heart, and veins carry blood to the heart. If you think about it in terms of oxygenation, you're going to wrong right here. The pulmonary artery carries deoxygenated blood from the heart to the lungs. The aorta is an artery that carries oxygenated blood from the heart to the systemic circulation. So arteries carry blood away from the heart, veins carry blood. So this is a vein, even though it's carrying oxygenated blood, because it's carrying blood to the heart. So let's break down the systemic circulation. Left ventricle. We're going to do it in order of blood flow. Left ventricle pumps. This is a muscle. So the muscle here contracts. Contraction of the muscle creates pressure. Pressure creates flow. Flow is what we're talking about. So the left ventricle contracts, creates pressure, forces blood into the aorta under high pressure. Why is it high pressure? Because this left ventricle is a very muscular, meaty, massive bit of muscle. The aorta divides into systemic arteries, some of which you have to know the names of. So for example, if you look at the key concepts list, you'll see that you're going to be responsible for knowing the names of arteries like the axillary artery and the brachial artery and the common carotid artery. Some of these are arteries that have names, and names is what anatomy is. And so some of these names you'll have to know. Aorta, systemic arteries that have names. These divide into tiny little arteries called arterioles that don't have names. There are too many of them, they're too small, they don't have names. They are named generically arterioles. The arterioles divide into microscopic tubes called capillaries. Now, again, there are billions of them, and we don't know that, we don't have names for them. But collectively, they're called capillaries. The capillaries then condense into tiny veins, but they're tiny, so they're called venules. The venules condense into veins, which have names, some of which are on your key concepts list. The veins join into the vena cava, and there's actually two vena cava. There's the inferior vena cava from the body, and there's the superior vena cava from the head, from the brain. So this cartoon is pretty weak here because it's showing only the inferior. This is really the inferior vena cava. It's not showing the superior vena cava. You'll see that in another slide. It's a little bit.
So it's from the body and
The inferior vena cava is from the body, and the superior vena cava is from the head. And then the blood goes into the right atrium, the receiving location for blood after it has gone through the body. Okay, so now let's continue and get into the pulmonary circulation. So now we're over here. Same general story. The right ventricle pumps the blood into the pulmonary artery, which goes into the pulmonary microcirculation, arterioles, capillaries, venules, that connect into the pulmonary veins that return blood to the left atrium. And now we're back where we started, because blood goes from the left atrium into the left ventricle. So these two slides take you in a very broad stroke through the circulatory system. At least most of it. Questions about this big picture? Yeah, awesome.
Will we be expected to be able to list the steps or the pulmonary and systemic circulation, or will we
I
get
think
into nitty-gritty?
both, actually.
Okay.
I think knowing the order
Mhm.
will come very naturally to you as you learn the anatomy.
Mhm.
So learning the anatomy, I wouldn't focus on memorizing the order yet, because I think that is going to become just dead simple to you when you start to think about the whole system. Other questions? So you may notice that the blood coming from the heart goes to various organs. Muscle, digestive tract, lungs. These are in parallel with each other, right? So some red blood cell here doesn't have a choice, but it either is going to go to this circulatory bed or it's not. And then it's either going to go to this circulatory bed or it's not, right? So these circulatory beds are in parallel with each other. It's not like this red blood cell goes through this circulatory bed and then is returned. It's not like it goes here and then here and then here. So the output from the heart, 100% of the cardiac output goes into the aorta. That's the only outflow tube. 100% of the cardiac output from the left ventricle goes into the aorta. And then some fraction of it goes to the skeletal muscle. And some other fraction of it goes to the digestive tract. And some other fraction of it goes to the kidneys. And some other fraction of it goes to your brain. So here is the fractions. I am not going to ask you to memorize these numbers. But it's interesting. Your brain, on average, gets about 15% of your cardiac output. When you're working hard mentally, it gets a little bit more. But even if you're, like in some Zen bliss state, your brain is still working pretty hard, and it's still taking a lot of the blood. It's still demanding a lot of the blood. And you might think, oh, when I'm sleeping, it's not taking as much. Well, sleep is a highly active brain time. Your brain is highly active even when you're sleeping. So there's times of high brain activity and not as high brain activity, but the brain is always demanding a large fraction of your cardiac output. The heart muscle itself, it's a muscle. It's receiving, through coronary circulation, a certain fraction of the cardiac output. Muscle, about a fifth, obviously up and down. If you're exercising, more. If you're relaxed, less. Skin, if you're exercising and your skin is trying to get rid of a lot of heat, a little bit more. If you're cold and your skin is, you've got goosebumps and you're trying to conserve heat, less. But, on average. Kidneys get about a fifth because you're using your kidneys to constantly remove toxins and other waste products. Digestive tract, more if you're digesting a meal, less if you're not, but on average. So you can see that the blood is being kind of evenly divided, 20%, 20%, 15%, 10%, to the various parts of the body that demand it. The typical cardiac output, so you're going to use this in the problem set. The typical cardiac output is about 5,000 mils per minute. I think in the problem set I used the number 4,700. Another perfectly normal, typical value. So I gave you the answer to this question. I told you that 100% of the cardiac output is going into the aorta. to go to the body. What percentage of the cardiac output is going to the pulmonary circulation or to the lungs? 100%. Every drop of blood that goes out this way goes out this way. Yep, that can't tell you how many medical students have tripped up on that trick question. But it's 100%. So I think this might be the last slide. Well, we'll see. So the left circulation, the circulation connected to the left side of the heart, is the high pressure side. Okay, so why is it high pressure? Because the left ventricle creates a lot of pressure in order to create the flow necessary to pump the blood throughout the whole body. The left ventricle is, you'll see it in anatomy lab this week. The left ventricle is a muscular, meaty, forceful pump. The right ventricle is less muscular, less meaty, because it's only pumping blood through one circulatory bed, the pulmonary circulation. So the left side of the heart is strong, and the right side of the heart is weak, less strong. But what's interesting is that in terms of where the blood is, where the volume of the blood is at any moment, the low pressure side, so let me back up. So the left ventricle generates high pressure. The right ventricle generates less pressure. The returning, the veins, contain the lowest pressure. So the pressure is high, and then the pressure falls as the blood is forced through the capillaries, well, through the arterioles and capillaries. So the blood flow in the veins is under low pressure, and it's not happening very fast. On average, well, that's not true. It's not happening very fast here, but it's happening just as fast here as it is here, right? Because it's the same blood flow. But it's under low pressure. High pressure, low pressure. In terms of where the blood is at any moment in time, about 20% of the blood is on the high pressure side, and about 75% of the blood is on the low pressure side. So we talk about the blood being high pressure, low volume, and low pressure, high volume. It's interesting. Most of your blood, more than half of your blood at any given time, is on the low pressure side of your circulatory system. Why is this important? Because it's a capacitive, it's a reserve volume for blood. You'll see, we're going to use this in about a week. Just hold it for now. Abby.
Are all 4 chambers under high pressure, or only the one to the right side?
Are all 4 chambers what?
Under high pressure.
No. Only the ventricles are under pressure. Under high pressure. So the atria are really receiving blood, and the pressure goes up and down in the atria, but it's the ventricles that generate pressure, and it's the left ventricle that generates the highest pressure. The atria will generate pressure because they are, you'll see, they are surrounded by myocytes, there is myocardium, there is contraction, but the pressure in the left and the right atrium, even when it contracts, is a tiny fraction of the pressure that's generated by the contraction in the left ventricle or the right ventricle. Let's see. Yeah,
Question about the capillaries.
okay.
So will our pressure decrease because of the large size of the capillaries? I mean,
Say again the question.
so will the pressure in the capillaries decrease because of the rising of the capillaries?
The pressure drops in the capillaries because the capillaries have each capillary has a very small diameter, so it has a high resistance. And because there's so many billions of them, they have a very large, let me get to that point. So I want to get to that point right now before we take a break. But this is an illustration of the branching, right? So I guess what I'm trying to illustrate is this cartoon is not so far off from what it really looks like. So this is actually the circulation in the heart itself. So here is an artery that's divided into two arteries, and coming off of this artery are thousands of smaller arteries, or arterioles, that then form a capillary bed, capillary mesh. Here is the answer to your question. So, and this is information you need for the problem set, for the question related to blood flow. It might be the last, I forget which question it is. It's the one that asks you, how long does it take for blood to flow through the aorta, et cetera. So, here's the schematic. Left ventricle, aorta, major arteries, minor arteries or arterioles, capillaries, microscopic venules, major veins, right heart, right ventricle, pulmonary artery, pulmonary circulation, back to the left side of the heart. Okay, so that's the schematic. Now, as we go across from left to systemic circulation, to right, to pulmonary circulation, back to left, the total cross-sectional area goes from something very low. So the aorta, you'll see it in the body, the aorta is about this big around. It's a circle, it's a cylinder, it's got a diameter. The diameter, and it's got a cross-sectional area. It's the area of a circle. It's about 4 square centimeters because the diameter is 2.3 centimeters in diameter, an inch or so. Notice what happens in the capillaries. The capillaries are microscopic in size. Each of them is microscopic in size, but there's so many billion of them that the total cross-sectional area is huge. The cross-sectional area of each capillary is microscopic, but you take a billion of them, this one plus this one plus this one plus this one plus this one, you know, the total cross-sectional area of all billion of those capillaries, and add them together, and the total cross-sectional area is 1,000 times greater than the cross-sectional area of the aorta. You need to know this number, and you need to know this number to do that question on the problem set. You don't need to know this number or this number, because we're talking about systemic circulation and not pulmonary circulation. So what I would like to do now is end with a movie of the heart. We're gonna end with one movie. Then I'm gonna send you to your breakout rooms to work on the problem set together. And then I'm gonna pick back up with this, with the anatomy of the heart in the second lecture. So let me show you this movie. And I think it's a pretty good summary movie. Oh, I just realized, so, okay, I'm gonna do one quick thing. What I just realized or remembered is that VGA does not have sound, and the movie has sound.
The normal heart
So this is an overview of where we're going after our problem set break. It's only a minute.
has two sides, a right side and a left side, and four chambers, the top receiving chambers, or atrium, and the lower chambers, which are thick-walled pumping chambers, called ventricles. Red blood cell will come from either the superior vena cava or the inferior vena cava and enter into the right atrium. The blood then flows across the tricuspid valve to the right ventricle. The right ventricle then squeezes and ejects that blood cell into a vessel called the pulmonary artery. Pulmonary artery splits into two vessels, each going to the lungs. As that red blood cell makes its way through the lung, it returns through the pulmonary veins to the left atrium. That blood is now oxygenated. It's picked up oxygen, then goes across the mitral valve into the left ventricle, which does most of the work in terms of delivery of blood flow to the body. That blood cell is now ejected into the aorta to some organ or muscle or skin in the human body.
Let's do that again. That is where we're going.
The normal heart has two sides, a right side and a left side, and four chambers, the top receiving chambers, or atrium, and the lower chambers, which are thick-walled pumping chambers, called ventricles. Red blood cell will come from either the superior vena cava or the inferior vena cava and enter into the right atrium. The blood then flows across the tricuspid valve to the right ventricle. The right ventricle then squeezes and ejects that blood cell into a vessel called the pulmonary artery. Pulmonary artery splits into two vessels, each going to the lungs. As that red blood cell makes its way through the lung, it returns through the pulmonary veins to the left atrium. That blood is now oxygenated. It's picked up oxygen, then goes across the mitral valve into the left ventricle, which does most of the work in terms of delivery of blood flow to the body. That blood cell is now ejected into the aorta to some organ or muscle or skin in the human body.
Now remember that this is describing, it says, it talks about the right heart and then the left heart. But you can see from the cartoon that both sides of the heart are pumping simultaneously. It's not like it's one and the other and then the other one. It's both of these hearts, both the left heart and the right heart, are pumping blood simultaneously. They're in series with each other. Okay, so let's go to your Zoom location. The Zoom link is on Moodle. So go to Moodle, get the Zoom link, go to Zoom. Let's reconvene at Zoom. How long will it take you to get to your Zoom location and get going? Give me a time.